Welcome to the fifth part of my video series on extinction events throughout Earth's history. Today, we are diving into the Permian Period, the final chapter of the Paleozoic era. When it comes to mass extinctions, the Permian is infamous for ending with the Great Dying, the largest known extinction event in Earth's history. But this wasn't the only crisis life faced during this time. The Permian was marked by multiple extinction events, making it one of the most turbulent periods to be alive. If you're new to this series, don't worry, this video stands on its own, but if you're curious about earlier extinctions, check out my playlist for a deep dive into Earth's most catastrophic events. Also, you'll find a document in the video description listing sources for images and research papers I used. Before we get into the extinctions, let's set the scene. The Permian period lasted for 47 million years, from 299 to 252 million years ago, bridging the gap between the Carboniferous and the Triassic. By this time, most of the Earth's land had merged into Pangaea, a vast supercontinent. The rainforest collapse that occurred during the Carboniferous had left behind massive deserts in the interior of the continent. The Permian was emerging from the late Paleozoic Ice Age, meaning ice sheets still covered the poles. This contributed to some of the lowest sea levels of the Phanerozoic Aeon. These extreme conditions shaped life in the Permian. While some organisms adapted to the drier climate, many struggled to survive. The changing climate favoured species that could survive without relying on water. Among plants, ferns and mosses declined, being replaced by the hardier conifers, cycads and ginkgos. Among animals, amphibians, once dominant in the Carboniferous, were losing ground. Since they needed water to breed and even to breathe, they were poorly suited to the increasingly dry climate. In contrast, amniotes thrived. The amniotes had one key advantage over amphibians. They lay amniotic eggs, which removed their need for water to reproduce. At this time, there were two main lineages of amniotes. The reptiles were still small lizard-like creatures during the Permian, although the archosauromorphs emerged late in the period. This was the lineage that would later give rise to the dinosaurs, pterosaurs, crocodiles and birds, but they wouldn't truly diversify or start to dominate until the Triassic period. The true rulers of the Permian were the Synapsids. These were the distant ancestors of mammals, although at this time they still looked very reptilian. You can easily distinguish them from reptiles by their skull structure, which had a single temporal opening behind the eyes, as opposed to the two seen in most reptile skulls. One of the most famous Permian predators was Dimetrodon, a sail-backed carnivore that grew up to 4.6 meters or 15 feet long. Many people mistake it for a dinosaur, but it was actually a synapsid, meaning it's more closely related to mammals, including humans, than it is to reptiles. Another major predator was the Gorgonopsians. These fearsome hunters may have used a strategy similar to modern Komodo dragons, biting their prey and waiting for it to weaken before delivering the killing blow. Early Gorgonopsians were small, but later species like Inostracevia reached lengths of 3.5 meters or 11 feet long. Among the largest animals of the time were the Dinocephalians. As another synapsid, they had a diverse array of species, including herbivores, omnivores, and carnivores. They often had thick skulls with bony projections, possibly for display or combat. Some, like Titanosuchus, reached up to 4.5 meters or 15 feet long and weighed around 2 tons. One purely herbivorous group was the Dicynodonts. They emerged during the mid-Permian and quickly became the dominant herbivores in many terrestrial ecosystems. They were found across the globe and ranged in size from rat-sized burrowers to elephant-sized browsers. Finally, one small but significant group of synapsids appeared towards the end of the Permian, the Cynodonts. First appearing around 260 million years ago, these creatures were minor players at the time, but they were the lineage that would later evolve into the mammals, a story we'll have to explore in a future video. The Permian was a world in transition, marked by dramatic climate shifts and evolving ecosystems, but this was just the beginning. The stability of this era was about to be shattered by a series of devastating extinction events. The Permian period experienced at least 3 major mass extinctions, although the exact number is still debated. The first and most controversial is Olson's extinction, which occurred around 273 million years ago. For decades, scientists believed there was a gap in the fossil record during this time, known as Olson's gap. It wasn't until 2012 that paleontologist Michael Benton and his colleagues helped debunk this idea, demonstrating the gap was actually a period of major faunal turnover. Even then, it remained unclear whether this was a true extinction event or simply a shift in dominant species. However, further research now supports the idea that a significant extinction event took place. Olson's extinction was particularly devastating for terrestrial vertebrates, especially early synapsids. Iconic predators like Dimetrodon, which had thrived in the early Permian, disappeared entirely. Other primitive synapsids, including many dinocephalians, suffered heavy losses but managed to persist a while longer. However, Olson's extinction paved the way for a new group of synapsids to rise, the Therapsids. Some, like the dinocephalians, were already present and suffered losses. Others, such as the Gorgonopsians, began to diversify and play a more dominant role in terrestrial ecosystems. While the Gorgonopsians first appeared around or just after this event, their reign, like many Permian groups, would come to an end before the period had concluded. Synapsids weren't the only ones affected. Plants also experienced a major shift, though not a large-scale extinction. The lush swamp forest of the early Permian, dominated by lycophytes, the relatives of today's club mosses and spike mosses, declined. These wetland-loving plants were likely holdovers from the Carboniferous period. But after Olson's extinction, they were largely replaced by hardier species, like conifers and other gymnosperms. Ferns and mosses still existed, but were much smaller and less dominant than their Carboniferous ancestors. The exact cause of Olson's extinction remains uncertain, but climate change is the most widely cited explanation. By this time, Earth had been undergoing a long-term drying trend that began at the end of the Carboniferous. This trend may have plateaued during the early Permian, only to worsen again, pushing ecosystems past a tipping point. The plant changes are particularly revealing. The decline of water-dependent ferns and mosses, alongside the rise of drought-resistant conifers, suggest a shift towards hotter, drier conditions. This supports the idea that Olson's extinction was not a sudden catastrophe, but rather a prolonged ecological transition. Some researchers speculate that volcanic activity could have played a role by releasing carbon dioxide into the atmosphere, triggering a period of warming. This warming would have accelerated the drying of wetlands and contributed to the vast inland deserts that characterized much of the later Permian. However, evidence for a large-scale volcanism during this time is limited, so this remains an open question. Olson's extinction is often overshadowed by later events, but it was a turning point in the Permian. It set the stage for the rise of the Therapsids, who would dominate the land, at least until the next extinction event arrived. Olson's extinction was just a blip in the fossil record compared to the turbulent times ahead. The Permian period was punctuated by 3 recognized mass extinctions, and these occurred so close together that life barely had time to recover before the next disaster struck. Just 11 million years after Olson's extinction, the world faced yet another crisis, the Capitanian mass extinction event. For a long time, this event was overlooked, mistakenly grouped with the more infamous End-Permian extinction. However, as fossil dating technology improved, it became clear that the Capitanian was a separate, distinct event. Though its precise timing is debated, it is likely it occurred around 260 to 259 million years ago. Once it was recognized as its own event, scientists realized just how severe the Capitanian extinction was. Some scientists even ranked it as the 3rd largest mass extinction in Earth's history, behind only the End-Permian and End-Ordovician extinctions. However, more recent research has lowered this ranking slightly. While not as devastating as the Great Dying, it was still a major catastrophe, particularly for marine life. Unlike Olson's extinction, which affected terrestrial life, the Capitanian mass extinction primarily targeted ocean ecosystems. Around 30 to 35% of known marine species disappeared at this time. One of the hardest hit environments was the shallow water reefs that teemed with life before the extinction. The crisis caused massive die-offs among sponges, corals, and other reef-dependent species. Some numbers paint an especially grim picture. 75 to 80% of corals vanished, and about 50% of sponges went extinct. It took millions of years for reef ecosystems to fully recover. Other marine groups also suffered heavy losses. Brachiopods were among one of the most severely affected groups, with entire families wiped out. Unlike some other lineages, they would never fully recover from this devastation. As for the bryozoans, these faced severe declines. This was most noticeable among the fenestrate bryozoans, which had delicate net-like skeletons. Other lineages were also affected, but they would rebound later in the Permian. Ammonoids were ancient relatives of squid and nautiluses. There was a complete collapse of goniotitic ammonoids. While the other primary lineage, the cerotitic ammonoids, would also be affected, that group would at least rebound to become a dominant lineage during the Triassic. Some echinoderms, such as the sea lilies and sea urchins, suffered heavy losses in shallow waters. While deep-water sea lilies survived, they never regained their dominance in the shallow seas. Sea urchins, however, were less affected and quickly rebounded, becoming key players in later ecosystems. The primary culprit behind this extinction was volcanic activity, specifically the emission traps in what is now southwest China. Around 260 million years ago, a series of eruptions blanketed the landscape in basaltic lava, forming a floodplain covering 500,000 square kilometers, an area about the size of Spain. These eruptions released vast amounts of carbon dioxide, sulfur dioxide, and methane into the atmosphere, triggering a chain reaction of environmental disasters. As greenhouse gases, these would instigate a period of global warming, coinciding with the end of the Paleozoic Ice Age. Warmer oceans hit shallow water species first, but this alone doesn't explain why land organisms were largely unaffected. The warming temperatures were combined with increased ocean acidification. When there is a large amount of carbon dioxide in the atmosphere, it will dissolve in seawater, forming carbonic acid. Do you notice anything similar about many of the organisms I listed as affected? They all use calcium carbonate. This could be the shells of ammonoids or brachiopods, or the skeletons of many corals, sponges, and sea lilies. Acidification weakens or dissolves calcium carbonate structures, making survival nearly impossible for organisms that rely on it. Lastly, there is also evidence of widespread anoxia or low oxygen in the oceans during this time. Evidence suggests the volcanic activity disrupted ocean circulation, creating dead zones with little or no oxygen. Deep water species were less affected since they were already adapted to low oxygen conditions. Shallow water species, which relied on oxygen-rich environments, suffered the most. Combined with warming temperatures and acidification, these factors caused the shallow marine ecosystems to completely collapse. The Capitanian mass extinction was a devastating event. Yet, in hindsight, it was just the beginning. At any other time, this would have been considered a major catastrophe, but in the grand scheme of the Permian period, it was merely a warning of the horrors to come. At last, we arrive at the End-Permian extinction event, also known as the Permian Triassic extinction, but more famously as the Great Dying. This was the worst mass extinction in Earth's history, occurring a mere 8 million years after the Capitanian disaster, around 252 million years ago. Just how catastrophic does an event have to be to earn a name like the Great Dying? In short, 96% of all species on Earth vanished. This extinction reshaped life on a planet in ways no other had before or has since. Like the Capitanian extinction, this catastrophe was triggered by volcanic activity, but on a scale far beyond anything seen before. This time, the culprit was the Siberian Traps, a vast volcanic province in what is now Russia, covering a staggering 7 million square kilometers or 2.7 million square miles. To put that into perspective, if the emission traps were the size of Spain, then the Siberian traps were almost as large as Australia, the 6th largest country in the world. Since we've already discussed the devastating effects of large-scale volcanic eruptions, carbon dioxide release, global warming, ocean acidification, and anoxia, there is no need to repeat them here. Simply put, everything that made the Capitanian extinction deadly was amplified many times over for the Great Dying. However, a few additional factors made this event even more catastrophic. The lack of oxygen in the oceans created the perfect conditions for sulfur-producing bacteria to thrive. These bacteria don't need oxygen. Instead, they breathe sulfates, which were in abundance due to the volcanic eruptions. Their waste product? Hydrogen sulfide, a toxic gas. As these bacteria flourished, vast amounts of hydrogen sulfide accumulated in the oceans. Eventually, this deadly gas escaped into the atmosphere, poisoning both marine and terrestrial life. While we have already talked about ocean acidification, the land was also likely ravaged by acid, in the form of acid rain. The gases released from volcanic eruptions, such as sulfur dioxide, would have reacted with the water vapor in the atmosphere. This is hypothesized to have been as acidic as lemon juice, and would have acidified the soils, severely affecting plant growth and survival, as well as further contributing to the ongoing acidification of the oceans. We often hear about climate change in modern discussions, but this event was a climate catastrophe on an unthinkable scale. Global temperatures skyrocketed by 8 to 10 degrees Celsius or 14 to 18 degrees Fahrenheit. Some regions became almost uninhabitable due to the extreme heat. Rising temperatures collapsed plant ecosystems, leading to widespread desertification across much of the land. As if the volcanic carbon dioxide emissions weren't bad enough, the intense warming may have destabilized methane hydrates on the ocean floor. Methane is an even more potent greenhouse gas than carbon dioxide, and its sudden release into the atmosphere would have triggered a second wave of extreme warming. This would have pushed already struggling ecosystems past the breaking point. Finally, the Earth's ozone layer, which protects life from the sun's harmful ultraviolet radiation, was likely severely damaged by the massive release of carbon dioxide, methane, hydrogen sulfate, and other greenhouse gases. With this natural shield weakened, radiation levels surged, harming everything from plants to phytoplankton and to all animals both on the land and in the sea. This would have been the final, crushing blow, ensuring that even the hardiest survivors were struggling to adapt. The Great Dying wasn't just another mass extinction. It was the Earth's closest brush with total ecosystem collapse. The combined effects of volcanic activity, climate change, ocean acidification, anoxia, hydrogen sulfide poisoning, methane release, and ozone depletion created the most hostile conditions life had faced since long before the Cambrian explosion. Now that we understand the extreme pressures facing life during this time, the 96% extinction rate doesn't seem so surprising. But let's take a closer look at which species disappeared forever and which managed to survive against all odds. The oceans were hit the hardest, with 90% of marine species being wiped out. Coral reefs, already devastated by the Capitanian extinction, completely vanished from the fossil record. Though a few corals survived, they wouldn't fully recover for 10 million years. Trilobites, which had endured since the Cambrian and survived many previous mass extinctions, finally met their end and completely disappeared from the fossil record. Conodonts, another Cambrian lineage, were mostly known for their strange tooth-like fossils, but like the trilobites, they would also vanish at this time. The sea scorpions were once dominant marine predators after appearing during the Ordovician. They had already been declining, but were yet another casualty of the End-Permian extinction. Some marine invertebrates did survive, but in drastically reduced numbers. Brachiopods, which were once extremely diverse, lost 96% of their species. There were thousands of species known during the Permian, but they have not been able to regain their previous dominance in the several hundred million years separating the Permian period from today. In fact, there are only 400 species alive today, a mere shadow of their former diversity. Ammonoids also suffered heavily, losing 98 to 99% of their species. On a positive note, the few survivors rebounded rapidly, diversifying within 1 to 2 million years and expanding into new ecological roles by the Middle Triassic. So, we have talked a lot about invertebrates, but how did the marine vertebrates fare? Sharks and rays were affected, but their adaptability and tolerance to low oxygen allowed them to recover quickly. Bony fish suffered major losses, particularly to the armored placoderms, which had been declining since the Devonian, but were now wiped out completely. However, ray-finned and lobe-finned fish survived and diversified in the Triassic. Mesosaurs, the first known aquatic reptiles, were lost. However, some other marine reptiles, like nothosaurs, survived and later thrived in the Triassic and Jurassic periods. Moving out of the water, land animals were not spared. Entire groups of dominant vertebrates disappeared forever. Among synapsids, the Gorgonopsians, Dinocephalians, and many therapsids were completely wiped out. The Cynodonts, though greatly reduced, survived and even thrived in the early Triassic. Lystrosaurus, in particular, became the most common terrestrial animal, making up over 90% of fossils found in some ecosystems. Cynodonts, the ancestors of mammals, also survived, though most early diversity was lost. These survivors remained small and nocturnal, staying in the shadows of the dinosaurs for the entirety of the Mesozoic era. Among amphibians, the temnospondyls were nearly wiped out, but a few managed to persist into the Triassic and beyond. Early reptiles suffered heavy losses. Scutosaurus, a dominant herbivore, disappeared, though some small burrowing parareptiles survived. The biggest winners of this catastrophe were the archosaurs, the ancestors of dinosaurs, crocodiles, and pterosaurs. Before the extinction, synapsids dominated, but with many wiped out, archosaurs rapidly diversified and took over the vacant niches. This dominance would last through the entire Mesozoic. Plants were hit hard, with many disappearing entirely. Seed ferns, which had survived the Carboniferous rainforest collapse, were now completely wiped out. Giant club moss trees and ancient horsetails dwindled to mere remnants of their former glory. Chordates, a conifer-like lineage, also went extinct. The loss of plant life was devastating for herbivores, adding starvation to the long list of extinction pressures. But a few groups managed to thrive in the aftermath. Ferns exploded in diversity, quickly taking over the devastated landscapes. Conifers, with their drought resistance, saw more long-term success. Ginkgos and cycads also survived and would become key parts of Mesozoic ecosystems. Finally, the End-Permian extinction is the only mass extinction known to have had a large impact on terrestrial invertebrates. Part of this is likely due to how rare terrestrial invertebrate fossils are, so our knowledge of their existence and evolution is quite incomplete. It should be a mark of how serious the End-Permian was that we do know how much of an impact it had on invertebrates. At least 8 orders went extinct, an unprecedented loss in biodiversity. To put this into perspective, modern insect orders include groups as diverse as moths and butterflies, or beetles. Losing just one order would be catastrophic. Losing 8 was devastating. Given the sheer scale of devastation at the end of the Permian, you might assume that life was doomed. But, as Ian Malcolm famously said,
life finds a way.
We have already looked at many of the species that would eke out a living in the post-apocalyptic world. Ferns and Lystrosaurus may have been the short-term winners of this struggle, but archosaurs would rise to become the planet's next dominant life forms, ruling the Mesozoic era. I hope you enjoyed this video. In the next installment of our mass extinction series, we'll enter the Triassic period, a time of struggle and recovery, where life barely managed to bounce back before facing yet another extinction event. Next week, we'll return to one of my channel's more standard videos, with a deep dive into a strange group of invertebrates known for their near indestructibility. Thank you for watching, and don't forget to share your thoughts in the comments below.